All right, this is a quick video, one more video for In Rem. So here's the premise. We have Nuuk, Greenland. We have Esperanza Base in Antarctica. The date is January 29th, 2018. Using timeanddate.com, the moon is visible in Nuuk for 7 hours and 47 minutes from midnight, and then for 10 hours and 23 minutes until midnight. This means that on this date, the moon is visible for a total of 18 hours and 10 minutes, or about 76% of the day. And the moon is not visible for a total of 5 hours and 50 minutes, or about 24% of the day. For Esperanza Base in Antarctica, the moon is visible for an hour and a half after midnight, and then for another about 3.5 hours before midnight. So the moon is visible for a total of 4 hours and 56 minutes, or 21% of the day, and the moon is not visible for a total of 19 hours and 4 minutes, or about 79% of the day. Using information from astropixels.com, the moon had passed through its descending node, which is when its orbital tilt is 0 degrees to the ecliptic, on January 18th at 14:28. And the moon passed through its ascending node, that's again 0 degree lunar orbit tilt to the ecliptic, on January 31st at 1846. The time between it passing the descending node and passing the ascending node is 13 days, 4 hours, and 18 minutes, which comes out to just about 19,000 minutes. So that means 1/2 of the moon's orbit, 180 degrees of its orbit between the descending and ascending nodes, was completed in 18,978 minutes. So if we know that's how long it took for 1/2 of the moon's orbit, we can figure out how long it took for 1/4 of the moon's orbit from its lowest angle, which is about 5.1 degrees below the ecliptic, to its appearance at the ascending node of 0 degrees. This would be completed in about half the time, so 9,489 minutes, or 6 days, 14 hours, and 9 minutes. So this is the same amount of time it takes for it to go from the descending node to 5.1 degrees below the ecliptic. So if we take January 18th, 1428, which is when it passed through its descending node, and add 6 days, 14 hours, and 9 minutes, we get January 25th at 4:37. And that is when the moon has reached negative 5.1 degrees to the ecliptic. That's what I have here. And we know that it was at 0 degrees to the ecliptic on January 31st at 1846. That's when it passed through the ascending node. So the time between when it was at 5.14 degrees below the ecliptic, January 25th at 4:37, and the time of January 29th beginning is 3 days, 19 hours, and 23 minutes, or 5,483 minutes. How much of the 90 degrees of its orbit did it travel in that time? We take 5,483 minutes and divide it by 9,489 minutes, and we get this fraction. Or we get this, this number between 0 and 1. So we estimate the angle of the lunar orbit that had been traversed between this date and this date, and we take negative 5.1 degrees and multiply it by 1 minus this fraction, and we get this value here of about negative 2.15 degrees. So I'm estimating that on January 29th, at 00, which is midnight UTC, the beginning of the day, January 29th in UTC, I'm estimating that the moon was about 2.15 degrees below the ecliptic. And then by the end of the day, I do the same sort of math, and I get that by the end of the day, it was about 1.38 degrees below the ecliptic. Averaging these out, I say the average angle of the lunar orbit versus the ecliptic was about 1.77 degrees below the ecliptic, and the average distance to the moon, using the average of these two values up here, was 223,124 miles. So, using all of this information together, I constructed this model over here. This model over here has the moon at a tilt of 23.4, because that is the tilt of the Earth, 23.4 minus 1.77 degrees. Okay? So the moon is, if we take 23.4 degrees as starting, that's when it's 0 degrees to our ecliptic. And then we subtract 1.77, so that means it's below the ecliptic. That's where I have the moon positioned, and it is positioned 223.124 units away from the Earth. There it is. I have everything at a 1,000 to 1 scale, a 1 to 1,000 scale. So now we have Nuuk up here. We have Esperanza down there. And what I've done here is I've made a line from Nuuk to the moon. I've actually made 2 lines, one to the leftmost limb of the moon and one to the rightmost limb of the moon. And basically, we have this dot that appears here, and that dot represents when the sight line touches the sphere of the Earth. So in other words, when the Earth gets in the way of our sight line. And I've marked on this line of latitude where those sight lines cross the sphere. So in other words, at these 2 blue dots, M and N, those are the limits where Nuuk cannot see the moon because its sight line goes through the Earth. So then I calculated the angle between M, the center of the Earth, and N, and this isn't the center of the Earth per se, this is the center of the circle that represents this line of latitude. So the angle from M to B to N is a little over 80 degrees. You can see that here. I did the same sort of calculation. Let me zoom out. I did the same sort of calculation for base Esperanza down here. Okay. Oops. Did the same sort of calculation for base Esperanza. So what I did is I basically figured out, where does base Esperanza not have its sight blocked by the Earth? So you can see that these sight lines to the moon are blocked by the Earth everywhere except between points S and R. And again, I measured this angle, and this angle is 66.63 or so degrees. So that's here. So my values were about 90% accurate. That is, given the percentage of the day that the moon was visible in Nuuk, 76% of the day, it wasn't visible for 24% of the day. So 24% of 360 degrees is 86.4 degrees. So the triangle up here should have been 86.4 degrees. I only had 80.15 degrees. So I was off by about 8%. And the same thing goes down here in Esperanza. The moon was visible 21% of the day, so 21% of 360 degrees is 75.6 degrees. I computed 66.63 degrees with my triangle. Again, I was off by about now 12%. So my conclusion is that it is plausible on the globe model for 2 places along the same line of longitude, but at vastly different latitudes, to have very different hours during which the moon is visible. My model was not able to exactly reproduce it. There are some potential factors that I have overlooked, such as the motion of the moon along its orbit, resulting in its distance changing over the course of the day by a few hundred miles. The changing angle of the moon, again, it started the day at 2.15 degrees below the ecliptic and it ended the day at 1.38 degrees below the ecliptic. In my model, I use a constant angle for the whole day. And there are some other options that I have not considered. So I haven't considered the differences between the perfect sphere, which I have in my model, and the imperfect sphere of the Earth. And I haven't factored in differences in elevation. If Nuuk is particularly high above sea level and Esperanza is not, or vice versa, those things could also have affected where the sight line to the moon is blocked by the Earth. So in conclusion, in Rem, I think it is perfectly possible for the globe model to allow for these two places which are on the same longitude to have vastly different times of the day during which the moon is visible. So that's that. I don't know if you will accept this model because it didn't match exactly. I don't know if you would accept the proof even if it did match exactly. But I'm glad that I got to make this model and do this experiment. I'm glad I got to try out this math. This was very interesting. I had to do a little bit of calculation for this, and I enjoyed doing it. So that's all. If I can't change your mind, it doesn't really bother me. I'm just glad I got to do this work. So enjoy the rest of YouTube.